Here is our lesson on the mean value theorem for derivatives. We'll learn about the mean value theorem, and mainly we'll look at the increasing and decreasing functions. Mean value theorem for derivatives states if y equals f of x is continuous at every point on the closed interval from a to b and differentiable at every point on the interval from a to b, then there is at least one point c in the interval from a to b at which the derivative of f prime at c, equals f of b minus f of a over b minus a. So what this tells us is where the derivative, which we know is represented by the tangent slope, equals the secant slope, which is the f of b minus f of a over b minus a, we'll have a point that we'll find. The point we're going to label as point C. Here's a representation of what we're looking for. Where the slope of the tangent line, that would be the line marked in pink, is equal to the slope of the secant line, that would be the line marked in black. Where those two are equal, have the same slope and are parallel, is what the value is that we're going to be looking for. Here's an example. Show that the function f of x is equal to x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Then find a solution to the equation where the derivative f prime at c equals the secant slope, f of b minus f of a over b minus a on this interval. The picture is to the right to show us what we're going to be looking for. Where do they have the same slope? Satisfying the hypothesis of the mean value theorem is our first part of the theorem. So if we review again the first part of the theorem asks us to show or figure out if it's continuous and differentiable. If it is, we can continue. So if we look at our function x squared, is it continuous? Yes. Is it differentiable? Yes. We can take a derivative. We're going to take the derivative. Derivative of x squared is 2x. I'm going to start by just plugging in x's. So 2x is the derivative. Set that equal to f of b minus f of a. Now the a to b interval in this case is from 0 to 2. So we're going to take f of 2 minus f of 0 over 2 minus 0. The derivative at the value that we're looking for, we'll figure out what that x is by solving it, and then we're going to call it c instead of x when we're done. So on the right you'll have a number, on the left you'll have a derivative, typically with x's in it. You'll solve for x and then just rename it as c. We're going to find f of 2 by plugging 2 into the function x squared. 2 squared is 4. F of 0, plug in 0 to x squared. 0 squared is 0 over 2 minus 0, which is 4 over 2. And that equals 2. I take the derivative, 2x, set it equal to the secant slope value, 2. Find where that occurs. Solve for x. At 1 is where that occurs. So my answer, and we can see that at 1, that the slopes are the same on the graph, we'll call it c equals 1. Next thing we'll look at are increasing and decreasing functions. Increasing and decreasing functions tell us about the behavior of the graph. What we're going to learn first about our functions are different types of behaviors. We've already learned that where the slope is 0, that would be at the top of the first black curve, and the bottom, where we have a minimum and maximum, slope is 0. And that would be at the bottom of the pink curve as well. So if these were individual curves, we're looking to see where the function is increasing and decreasing. So if we take a look at this first black curve, we can see that the function is increasing, then decreasing, and then it's increasing. Where the function again had slope of 0 is where it changes direction from increasing to decreasing. Those are always going to be, as we talked about, your minimum and maximum values. So how are we going to find functions that are increasing and where functions are decreasing? By just knowing the derivative. The idea is that if we're given a function, we can use the derivatives to find where the function itself is increasing, decreasing, or if all we know is the derivative and we can't get to the function, we can still find where the function is increasing, decreasing. What we'll be able to tell then is where the function is 0 has a min or max, where the function is going to be positive or negative, it will be increasing and decreasing. So what we define is the idea of what makes a function increasing. We know that from left to right, the f values, it says f increases if the f of x, which are the y values, are getting larger, decreases if the y values are getting smaller. So by definition, for derivatives, if the derivative is greater than 0 or positive, in other words, so this is going to be the first one, positive, and where the derivative is less than 0, so that's where the function, or sorry, the derivative, not the function, is negative, we can tell then increasing, decreasing. So derivative positive or greater than 0, function would be increasing. Derivative is less than 0 or negative, the function would be decreasing on the interval from a to b. So here's an example to follow. Where is the function increasing and decreasing? So we know the function is increasing where the derivative is greater than 0 or positive. The function is decreasing when the derivative is less than 0 or negative. We'll take a look first at the derivative. The derivative of the function (2x to the third minus 12x) would equal 6x squared minus 12. We want to figure out where the function is positive and where the function is negative. So what I'm going to do is figure out where the derivative is increasing and decreasing by solving for x. First, if I can figure out where the minimum and maximum are, and then that's my point where it changes direction, I should be able to figure out where the derivative is positive and negative. So I'll solve this and set it equal to 0 first. 6x squared equals 12, divide by 6, x squared equals 2. Square root it, x is equal to plus or minus the square root of 2. So those are the points where it's going to be having a minimum or maximum. It's going to be a critical point, is what we're going to eventually learn it as being called, both points actually, and then we're going to solve for where the derivative is positive and negative. So our interval is going to be divided up into negative infinity to negative square root of 2, negative square root of 2 up to positive square root of 2, and then positive square root of 2 up to infinity. We'll eventually look at using sign charts, and so we can discover then what happens to the function as we're describing the behavior of the derivative. So here's what we can determine. If I take a number that's in the first interval, and that would be from negative infinity up to negative square root of 2, pick a number and plug it into the first derivative function to see what's happening. Where's the derivative positive and negative? So we'll kind of keep track as we go. If we pick a number, for example, that's much smaller, pick something that you know for sure is smaller than negative square root of 2, so like negative 10 for example, square that, it would be 100 times 6, so 600 minus 12. We know that's going to be positive. So we know that in that interval between negative infinity and negative square root of 2, the function will be increasing because the derivative is going to be positive. Between negative and positive square root of 2, easy one to check is 0. 0 squared is 0 times 6 is 0. Minus 12 would be negative 12. That was negative, so that's down on the decreasing side. So negative square root of 2 to positive square root of 2 is the function decreasing because the derivative is negative. Then we pick square root of 2 to infinity. So again, pick something like 10. 10 will actually give you the same answer as negative 10 when you square it. So we know that's going to be positive, which means the function will be increasing from square root of 2. So here we'll use a little union symbol to infinity. At the points, you don't include them because at the points is where it's changing direction and you have some kind of a minimum or a maximum value. Here's another example. Y equals x squared. Where is the function increasing and where is it decreasing? Here's something that we'll know by looking at it. We know that x squared is a basic parabola function. So if we graph it, just to kind of sketch and see what's going on, we can tell where the function will be decreasing and then increasing. Let's check by the derivative. Derivative f prime of x is 2x. Again, look for the points where the min and max are. We can see that will clearly be at by the graph and by our work at 0. So we're going to look to the left and to the right of 0. Negative infinity up to 0 and then 0 up to infinity. Plug in numbers in each of those intervals into the derivative. Here's what we get. Plug in, for example, anything smaller, so negative 1, so the answer would be negative. So we know that the function, if it's negative or less than 0, is the function is decreasing. That would be from negative infinity up to 0. The function would be increasing where it's positive. So if you put in a number bigger than 0, like 1, it's positive. So the derivative is positive or greater than 0, which means that the function is increasing when the derivative is positive from 0 to infinity. Look at the graph up here. We can see that it goes decreasing up to 0, then you have a minimum, and then from 0 to infinity, it's increasing. So remember that we're describing the behavior of the function by using the derivatives. Here's another example. Where is the function increasing or decreasing for x over x squared minus 4? So first thing I'm going to do is factor the denominator and take a look at it for a moment just to see what's going on with the function. We can see some different things here happening with this. It's a difference of squares here, so we can see that you're going to have what appears to be here some asymptote lines where the function is actually going to be undefined. Let's find the derivative first. We're going to use the quotient rule. So we have v times derivative of u minus u times derivative of v all over v squared. Simplify. X squared minus 4 minus 2x squared all over x squared minus 4 quantity squared becomes negative x squared minus 4 over x squared minus 4 quantity squared. What we're focusing on here are two things. We're going to figure out that the critical points or our important points on the graph are going to be where the numerator is equal to 0, and so we're going to check that, and where the function is undefined. Let's start with this. Negative x squared is equal to 4. X squared is equal to a negative 4. So what we're going to notice for this problem is that at a certain point here when we're solving it, we notice that, first of all, again, from the original function, at negative 2 and at positive 2, we're going to have some vertical asymptote lines, or where the function is undefined. And so then we're looking at the part down here now, focusing on this, we can see that there is no real solution here for where the function is equal to 0. So what we're going to do, and they get the same values, by the way, if you plug in 2 and negative 2 into the derivative, you get a 0 down in the denominator. So what we're going to actually check it against is from using 2 and negative 2. That's from where the denominator is equal to 0 or undefined. Okay, because this isn't going to work. So then I check anything smaller than 2 into the derivative, and anything or smaller than negative 2, between negative 2 and positive 2, and anything bigger than positive 2, to figure out where the function is increasing and decreasing. So if I pick a number like negative 3, for example, negative 3 squared would be 9, and opposite of that would be negative. Minus 4 is still negative. And then in the denominator, no matter what we squared, it's positive. Negative divided by positive is going to be negative. So between negative infinity to negative 2, it's negative, which means the function will be decreasing. Then from negative 2 to 2, we check 0, easy one to check. 0 minus 4, negative 4, over 0 minus 4 squared is going to again be positive. So again, that's going to be negative. So we're still decreasing from negative 2 to positive 2. And then we check something bigger than 2. Again, for example, we can check a positive 3. Positive 3, because of the negative outside here, is going to have the same effect as negative 3. So that means that if we put in a positive 3, we're going to still have a negative number, which means, again, we're still decreasing. Now remember that you can't list them as one interval, because at negative 2 and 2 you have vertical asymptotes. So this is how we would list it. Switching gears a little bit, we're looking at the first derivative for each of the following to take a look at some different types of functions that we might encounter as we're talking about functions increasing and decreasing. So if we look at each of the derivatives here, this would be the first one. We'd have a 6x plus 2. Second derivative, 6x plus 2. Next derivative, 6x plus 2. Next derivative is 6x plus 2. Point here is that it doesn't matter what the constant is that we're adding or subtracting. Here we're not actually adding anything. It would be like saying plus 0. We get the same derivative. So how are we going to know what the constant is that we're adding or subtracting? Because you get the same derivative. So the idea is for increasing, decreasing, remember that we're using the derivative to describe the behavior. How do we know where the function is going to be? At what point on the graph are we starting? Or what point are we ending, and where are we? So we're going to look at the idea that if we have a constant c, capital C stands for the constant for which the function has a derivative at 0 on the interval, that the same derivatives are going to differ by that particular constant, whatever that number is. So just like we looked at, you're going to have a whole bunch of functions that are going to differ only by the constant that have the same derivative. We're going to give it a name. It's called the antiderivative of the function. We use capital F for antiderivative, so be careful with that now. That stands for antiderivative versus the function is regular f of x. And that we say that if we're going to take and go backwards from the derivative to the function, it is called antidifferentiation. Here's an example. Find the function whose derivative is given that passes through the point 1, negative 2. I'm first going to take this and move it up to the numerator. So I have 1/4. I'll write this first piece as a fraction, x to the negative 3/4. We have to figure out a function that this is the derivative of, so let's think backwards. To get the derivative, we brought the power down in front, and we're going to subtract 1 from the power. So for this one, I'm going to do the opposite. I'm going to add 1 to the power. Now watch what happens when I do this. When I add 1 to the power, so I'm adding 4/4, I get x to the 1/4. Think about this now the other direction. If I take the derivative of x to the 1/4, it would be 1/4 x to the negative 3/4. Well, that's what we have right here. So this is going to have a big old plus c now, because we don't know the constant. To find the constant, I'm going to actually plug in this point. So I have y equals x to the 1/4 plus c. Plug in the point for x and y. Negative 2 equals 1 to the 1/4 plus c. And let's solve for c. 1 to any power is 1. Subtract 1 from both sides. Now I know if I'm passing through the point 1, negative 2, that my constant is going to be negative 3. So my function was x to the 1/4 minus 3. That's worth the derivative of the original up here at the top. Last example, finding velocity and position, dealing with again, knowing the acceleration. So this is just another example of working backwards. If we know what a of t is 9.8 and v of 0 is 0, we know the velocity at 0 is 0, and we know that the a of t is 9.8. Here's what we figure out. We know that if we take and work backwards, antiderivative of 9.8 would just be 9.8x, in this case 9.8t, plus c. Plug in the 0, so c is actually 0. The velocity function would be 9.8t. Going one step back further, antiderivative of 9.8t, again think of add 1 to the power, what number would I need in front? That would be 4.9, so when I bring down the 2, I get a 9.8. So 4.9t squared plus c, again plugging in the, kind of like thinking x and y here, 0 and 0, you get c is 0. So the position function will be 4.9t squared. We'll do a lot more with these kinds of functions when we start studying the next chapter, chapter 5. So for now, we'll just do some very simple ones to help us get through the types of problems we're solving. That's our lesson for today.